All right, in this section, we're going to look at differential equations and how they work and some other kind of cool related items. So the first order of business is to talk about what a differential equation is. And a differential equation is just some sort of equation. It doesn't matter what kind of equation, except that it needs to have a derivative in it. And the order of the differential equation is the order of the highest derivative that's involved. So when you're looking at different things, how can you tell what the order of highest derivative is? Well, it would be something where you would have, like, say, d squared y dx squared. This would be a second order. Or if you were looking at something that said, like, y primed 3 times, okay, that would be a third order. So when we're doing this problem, the problem that we're going to look at today, all we're doing is we're going to look at this guy right here. And he's a first order differential equation. So what do we want to do? We want to solve this guy. And how do you undo derivative? You integrate. So if we multiply, this is kind of neat. If we have this derivative, and you multiply both sides of this equation by dx, then what you end up with is a situation where you have dy equals, the change in y equals all of this stuff, secant x squared plus 2x plus 5 times the change in x. And then if you go one further step and you integrate both sides, okay, so on the left side we're going to have some sort of y variable. On the right side we've got all x variables. Well, if you integrate dy, you're going to get y. So there you go. There's our equation, okay? If we integrate the left-hand side, then what we're wanting to say is the derivative of what thing is secant squared x. Derivative of what is secant squared x. And the derivative of tangent x is secant squared x. The derivative of what is 2x, and that would be derivative of x squared. Okay? The derivative of what is 5, and that would be 5x. And you can check, the great thing about integration is you can take the derivative of all of these things right here and find, and if you can get back to where we started up here in this kind of brownish reddish color, if you can get back to where you started, you've done the right thing. And remember, when you're taking derivative, think about, with your trig functions, derivative of what trig function will be secant squared. And you can look at a chart and tell. Or with derivatives, when you take derivative of x, remember you subtract 1 from the exponent. So we know we have to add 1 to the exponent. So those are kind of some tips and tricks to get us started. Well, we want any equation that can satisfy that. So we have to add a constant out here at the end, because the derivative of every constant is 0. And to allow for all the possible functions of y that satisfy the equation dy dx equals, then we have to add the c over there. That way we can include every constant that we can think of, and we can still get to the correct answer. So there's a differential equation. What it boils down to is integrating both sides. All right, so here we've got an initial value problem, and this is super similar to the one that we just solved out. So it says find the particular solution to the equation dy dx, where e to the x minus 6x squared, whose graph passes through the point 1, 0. Well, now what? We want the original equation that goes to this specific point. Anytime we're given a point, we're always given a value for x and y, and it's very important to remember that. So let's take a look at this differential equation that we've been given. dy dx is equal to e to the x minus 6x squared. And again, if we multiply both sides by dx, then what we're going to find is we have a setup where we've got dy equals e to the x minus 6x squared dx. And again, we're now ready to integrate, and we can integrate this. And remember, when you integrate dy, it's just going to go to y on the left, and when you integrate the right-hand side, those will have your x variables. So when we do this integration, we're going to get y equals, and the derivative of what thing is e to the x. And this is the easiest guy to take derivative of because the derivative of e to the x is e to the x, all right? Minus the derivative of what thing is 6x squared. Well, remember, when you take derivative of a function and you have exponents in it, you subtract one from the exponents. So what we're going to do is we're going to add one to the exponent. Now, ask yourself a question. 3 times what number is 6? And that would be 2. And then don't forget that we have to have a constant over here at the end. So this is our antiderivative. This is solving the differential equation for any possible thing. But they gave us, right here, they gave us a starting point, an initial condition. So how can we go ahead and solve this out? Well, y becomes 0, e to the x, e to the first, minus 2 times 1 cubed plus c. And so now all we have to do is just solve this out for c. So 0 equals e minus 2 plus c. Go ahead and add 2 and subtract e. And you get this for the constant. And you know what? That's okay if e is in our constant. You don't need to decimal this out. You can just leave it alone. And so our final answer for this particular problem would be this function right here, e to the x minus 2x cubed, plus that constant right there. So we would say that y equals e to the x minus 2x cubed plus 2 minus e. And that would be the equation, and that's an okay answer to have. There's nothing wrong with that at all. So there you go. That's an initial value problem where you solve out a differential equation through a specific point. All right, find the particular solution to the equation dy dx equals 2x minus secant squared x, whose graph passes through the point 0, 3. And you'll notice that on this particular one, secant squared is going to have several discontinuities where you've got vertical asymptotes. Don't panic. As long as we are looking at a point that is actually on the graph, we should be able to work this out. We would just look at that particular place on the graph, that particular interval where things happen correctly. So here we go. Dy dx equals 2x minus secant squared x. Multiply both sides by dx. And what you're going to end up with is dy equals 2x minus secant squared dx. And we can integrate. So this is actually no different than solving out for y in your former algebra life. You're just getting that y part all by itself, but we're adding to our bag of tricks now, integrating. And instead of multiplying or dividing both sides or using a logarithm or something like that, something that you've done in the past to isolate the y, we're now going to add this integration to that. You end up with then y equals, and then think about this, x to what power? So this was first power, so x squared. Derivative of this has to be 2, so it would just be x squared. And then derivative of what is secant x? And the derivative of tangent x is secant x plus c. So now we're talking about like tangent x. Well, remember that with the tangent, we've got sine over cosine. So when we combine those graphs together to get our tangent graph, remember that we're going to have asymptotes at pi over 2. And that our graph is going to look something like this. We're going to go through 0 here. At pi over 4, we're at 1. Negative pi over 4, we're at negative 1. So it's a graph that looks something like that. Okay. The reason I draw the tangent graph is we know that x squared is defined everywhere. So if we look at x squared, if we look at this graph, we're looking at this situation. So we're looking at a combination of these two things. Here's the deal. We need to be defined at 0. 0 is the x-coordinate. We need to make sure we're not on an asymptote, and the tangent determines where that asymptote is going to be. Okay? So when we're looking at 0, if we look at both of these graphs at 0, we are defined at 0 on both. That doesn't mean we'll be 0. We could be, but we know that we're okay there. So what do? Well, we use the old rule that if they give me a point, they've given me an x value and a y value. So I'm going to plug in a 3 for my y. I'm going to plug in zeros for x's. And I'm going to solve this bad boy out. So this is going to be 3 equals 0 minus tangent of 0, 0 plus c. And as it turns out, they both are 0 at that spot. And so how do we finish this guy up? Well, we use this part of the information that we discovered through antiderivative, and we use this guy down here as the constant. So y equals x squared minus tan x plus 3. So there you go. There's dealing with a discontinuity. And if we had been over here someplace with tangent, remember it's periodic and it repeats. So if we had been over somewhere in this space, we would just need to have checked to make sure that this point could be a possibility to lie on that line for the x-coordinate. Okay, we're going to find the solution to the differential equation f prime of x equals e to the negative x squared, for which f of 7 equals 3. The one rule I'm going to give you on this one is we want to use fundamental theorem of calculus. Okay, and remember when we did that, we had the integral and we went from 0 to x of t squared dt. And remember, this became x squared. So on our problem, when we're looking at this, here's that inside the integral part, and it would be negative t squared here, dt. Here's our x value that we're going to start at here. Here's the x for the fundamental theorem part, and then plus 3. And remember, with fundamental theorem, this was a y equals situation. If you just rewind a couple lessons, this is how the fundamental theorem works. And if you think about it, if you take the derivative of both sides, then we would have dy dx is equal to dy dx of this equation and remember, we're just talking about derivative of just everything over here. So derivative of the integral then just becomes e to the negative x squared. Remember that the derivative of 3 becomes 0, so there's our f prime. It really is just that simple. It really is just that simple. Don't make it super hard. Just follow the pattern, and as you follow this pattern, things will start to click into place. All right, this is kind of a fun little problem to do, and it's graphing a family of functions. So when we have dy dx equals cosine x, we've got dy dx equals cosine x. And remember, if you multiply both sides by dx, then what you're going to have is dy equals cosine x dx. And we can take the integral of both sides. All right. Once we've taken the integral, we end up with y equals sine x plus c. Now, it says graph the family of functions that solve that differential equation. And so what that means is we're going to graph every possible example of sine x plus c. And how do we do that? Well, we start with the sine curve. And sine curve looks something like this. And it continues this way. Okay. And all that means is that we're going to graph another sine curve above it. And if you look at the calculators that I have up right now, you'll notice that there's some really cool ways that you can do this on your graphing calculator. And this is graphing all the possible functions that could give us a derivative of cosine x. Remember, if all you have is that constant, the derivative of a constant is 0. And so that's how this works, and it's really kind of a neat thing when you put it on your calculator. Now pay attention, there's a couple of special keystrokes in there. If you're on an 84, you can store a specific list, and then you can use that list as your x values. You can do it on Inspire too, and I'll have a separate video on exactly how to do that, or if you can see the keystrokes here, you can use it as well. But so there you go. There's graphing a family of functions. All right, on this problem, what we're going to do is we're going to look at what's called a slope field, and basically a slope field is best summed up by this: remembering that any differential equation is the equation to find the slope at a point of the original function. Then we can use that equation to create several small linear approximations that resemble the many different functions that are in a family of solutions. So construct a slope field for the differential equation dy dx cosine x. What that means is we want to come through and find the slope that leads to cosine. You know, where did we start? We started at sine. Okay, and if we have y equals sine x, and we take the derivative of that, we get to cosine x. So what a slope field does is it looks at all these little points all the way across the x-axis, and it creates this infinite number of little tiny linear approximations. So here's a linear one, here's one, here's one, here's one, here's one. And they follow, can't see that guy in there, he's in there somewhere. They end up following the equation for the sine curve. And it's an approximation. It's little bitty linear strips of line. And they go together to create this field. And you can look at slope fields and determine what the function that you're looking at is. And so what I did was I graphed with the Inspire, and I will have a separate video on graphing because it's a little bit different. But I graphed on the Inspire the slope field for the cosine of x. And remember, if you integrate cosine x dx, you end up with sine x plus c. And so our slope field, all these little linear lines, should look like the sine curve, should resemble the sine curve. And if you kind of, you don't even have to cross your eyes too much, but you can kind of see a sine curve in here that you could trace out fairly accurately by following all the little slopes. Okay, and that's how it works. Now, if you're using an TI-83 or TI-84, there's a fairly somewhat complicated program that you will need to plug into your calculator, and you can search that out on the internet and do it. But there's a fairly complicated program that you'll want to use to help you with these slope fields. But gosh, it's a really nice program to have. So if you're in my neck of the woods, I've got a copy of it. And if you're not in my neck of the woods, just Google how to program your calculator on a TI-83 or 84 with a slope field in it. So there you go. That's how you look at a slope field on your calculator and what it means. Okay, Euler's method, the last little guy that we're going to work on here in section 1, and it's basically using what's called local linearity, and you're going to look at a specific point or specific area and on your graph, and you're going to look at what's going on really close to that specific value of x. Okay, and so Euler's method is similar to a slope field in that it takes any curve that you're looking at and stretches your curve into some sort of linear shape. The closer you are to a specific point, the easier it is to get that linear shape. So what we're going to do is we're going to let dy dx be equal to x plus y. We're going to let f of 2 equal 0, and we're going to use the increments delta x equal 0.2 to approximate f of 3, okay? And this is going to give us a particular solution to a differential equation, okay? Remember, this is a differential equation because it's got a derivative in it. And we're going to look for an approximation, a really good approximation to what happens at our function when f is 3. Okay, so here we go. X and y. Well, anytime we're given this information, we're given x and y. So x is 2 and y is 0. So then just follow this rule right here. dy dx is x plus y. Okay? Delta x, they already told us, is 0.2. Delta y is dy dx times delta x. So 2 times 0.2 is 0.4. And then you add delta x and the delta y. So delta x was 0.2, so that's going to give me a new coordinate now of 2.2 and a y coordinate of 0.4. So all I did was I took my x coordinate of 2 plus 0.2 and my y coordinate of 0 plus 0.4. And we're going to fill the chart in this way, and we're going to get to a really good approximation of what's going on when x is 3. So my new xy is 2.2 and 0.4. And so I add them together. That's going to be 2.6. I multiply by delta x, which is 0.2. So if you'll just humor me, I like to double check myself on this, because if you get off early on, then you'll be off the rest of the time. So I get this guy to be 0.52. So when you add, you're going to do 2.2 plus 0.2, that's going to be 2.4. And then you're going to do 0.4 plus 0.52, which is 0.92. Okay, and now I've got a new y value. Remember, we're going for that particular solution, a specific point. So now I've got 2.4 and 0.92, and I add those up, and that's going to be 3.32. And I add them up because that's what it's telling me to do with x and y. If it says x times y, then you would multiply them. If it said 2x plus 3y, then you would do that. So whatever this rule is what you do with your x and y coordinates. I'm going to take that 3.32 times 0.2, which is going to be 0.664. And then add all these up. So my 2.4 now becomes 2.6. And my 0.664 plus 0.92 becomes 1.584. And that's my new starter. So 2.6 and 1.584. I'm going to add those together. I'm going to multiply by 0.2, which is 0.8368. And then I'm going to add all that stuff together. So 2.8. Now we're getting really close because remember we want f of 3. So 2.8 and 1.584 plus 0.8368. So this is going to be 2.42 all right, and then come back over here, and this should be the last row. So 2.8 and 2.4208. Add those together. 5.2208. And please double check me as I go. I can sometimes get off track on this chart. This can be a bit tricky. So 1.04416. I'm going to carry through all the decimal places because I want to be as accurate as possible. So here we go. 2.8 plus 0.2 is going to be 3. And the y-coordinate, which is what we're really interested in, is going to be this 1.04416 plus 2.4208. And 46496. Okay, so the answer to this question then, this is what we're really interested in, this is what we really want to know, is going to be 3.4649. As long as I didn't make an error somewhere in all of my adding and subtracting. But Euler's method is not super hard, and it lets us look at what's going on at a pretty narrow part of the x-axis. And it's just a pattern-based formula. So you just do exactly what the top of each column says, and you should be good to go without any problems.